Welcome to this lecture of hyperbolic geometry. In this lecture, we'll prove that if you take a geodesic triangle in upper half plane with respect to hyperbolic metric, then the area of the triangle will be equal to pi minus sum of the vertex angles. So in order to prove this thing, we'll be needing the some fact about complex analysis. So like an analytic function satisfy Cauchy-Riemann equations. So let us begin. First, let me define. So what do you mean by hyperbolic area? So let us take a subset A of this upper half plane. And again, note that this upper half plane, it is equipped with this hyperbolic metric. So we define mu A. So the hyperbolic area of A by this double integral dx dy by y square over this A, provided this integral exists. So our next job is to prove that if you take an isometry of this upper half plane, so then it preserves the area. So if I take an element of this PSL to R, so it will preserve the area. So in order to do that thing, so I'll be needing a fact that an analytic function, it satisfies Cauchy-Riemann equation. So let us recall that thing. So what do you mean by Cauchy-Riemann equation? So let me write down Cauchy-Riemann equation. So an analytic function fz equals to uxy plus ipxy, where z equals to x plus iy, it varies over a domain. Satisfies Cauchy-Riemann equation. So what is this? That is, so if you take the partial derivative of u with respect to x, so this is equal to partial derivative of b with respect to y, and the partial derivative of u with respect to y is equal to minus of partial derivative of b with respect to x. So these are Cauchy-Riemann equations. So I'm sure that you have seen this thing in complex analysis, so I'm not going to prove this. Okay. So now the theorem is the following. So let us take a subset of this upper half plane such that so mu of A exists. And now let us take an element of this PSL to R. So then this mu of T of A, so this is equal to mu of A. So what is the proof of this? So let us take T to be of this form, Tz equals to Az plus B by Cz plus D, where this AD minus BC is equal to 1, and this A, B, C, D are my real numbers. And let us take z to be equals to your x plus iy, and we can also write tz equals to uxy plus ibxy. This t, it is also an analytic function. So t is an analytic function. So therefore, this t will satisfy the Cauchy-Riemann equations. So t satisfies Cauchy-Riemann equations. Okay, so that is del u del x is equal to your del v del y. Del u del y is equal to your minus del v del x. Now, so if you compute this Jacobian, so the Jacobian, so which is nothing but, so it is denoted like this, and which is nothing but, by definition, it is the determinant of del u del x, del u del y, del v del x, and del v del y. So this is equal to your del u del x square plus del v del x square. So this you get by this Cauchy-Riemann equation, because del u del x is equal to del v del y, and del u del y is equal to minus del v del x. So determinant of this matrix will be equal to del u del x square plus del v del x square. So this is basically equal to your del u del x plus I del v del x. You take the mod of this thing, complex number, and take the square. Okay. So also note that, so tz we have taken to be your u plus ib. So t prime z, so this also a fact. So t prime z, it is equal to your del u del x plus I del b del x. So t prime z is del u del x plus I del b del x. So I'm sure that this computation also you have seen in complex analysis course. So therefore, so from this equation star, so what we are getting, so this Jacobian is equal to your mod of t prime z square. Okay. So also this tz is equal to your az plus b by cz plus d. And now if you compute this t prime z, so what will be this thing? So this will be equal to your, so cz plus d square, and here you're taking the derivative of the numerator, so it will be a times cz plus d minus az plus b times c. So ad minus bc is equal to 1. So the numerator will be equal to your 1. So we have this thing here. So therefore, so this Jacobian, so this will be equal to 1 by, take the mod of cz plus d, and take the power 4. Okay. So again recall that tz is equal to your u plus ib. So therefore mu of ta, so this is this integral, double integral, integral over ta du dv over this divided by b square. So this is equal to, so t is a map from this upper half plane to upper half plane. So this integral, so this will be equal to integration over a. So you take the Jacobian times dx dy by your b square. So this du dv, So this is equal to the Jacobian times your dx dy. So now this right hand side integral, so this will be equal to your integration over a. So the Jacobian already we have computed. So this is 1 by mod of cz plus d equal to the power 4. And what is my this b square? B is the imaginary part of this dz. So b is the imaginary part of dz. So then I have to do a computation. So tz is equal to your az plus b by cz plus d. So this is equal to your az plus b by mod of cz plus d square. And then in the numerator, you have this multiplication, the conjugate of this cz plus d. So we have this thing here. So cd are real numbers. So this is equal to az plus b by and multiplied by c z bar plus d divided by mod of cz plus d square. So now if I take z equals to x plus iy, so this dz, so this will be equal to your a mod z square plus bd plus bc x plus adx plus iy 8e minus bc whole divided by mod of cz plus d square. So therefore, so this b equals to imaginary part of dz. So this is equal to your y by mod cz plus d squared. So here this ad minus bc is equal to 1 because we have taken this t from this PSL to R. So ad minus bc is equal to your 1. Okay. So now from this equation, so this mu of ta, so this will be equal to your, so 1 by cz mod of whole to the power 4 times dxy y divided by b square. So from this equation, so what you have, so mu of dA, so this is equal to your integration over a 1 by mod cz plus d to the power 4 times, so b is equal to y by mod cz plus d squared. So therefore, so here we have this thing. So which is nothing but equal to your integration dx dy by y square over a, and which is equal to your this mu of a. So therefore we have proved that, so if I take t from this PSL to R, so that is an isometry of this upper half plane. So mu of ta is equal to your mu a. Okay. So now the next theorem is the following. So area of a triangle is equal to pi minus the sum of the vertex angles. So this theorem is also called the Gauss-Bonnet theorem. So area of a geodesic triangle in this upper half plane. So what is the statement? So let delta be a geodesic triangle in this upper half plane with vertex angles alpha, beta, gamma. So then the area of delta, so that is that we have denoted by mu delta. So this is equal to your pi minus alpha plus beta plus gamma. Okay, so by a geodesic triangle, we mean a triangle in this upper half plane whose sides are geodesics. So let me draw a picture. So this picture, it is in the upper half plane. So this is my triangle delta, and the vertex angles, suppose these are alpha, beta, gamma. So then it is saying that this area of this triangle, so this is equal to your pi minus alpha plus beta plus gamma. Okay, so what is the proof of this? So case 1, so what we are going to do, so in case 1, so we are going to take a vertex of this triangle delta in the real axis, or it can be infinity also. So let one of the vertices of delta lie in this R union infinity. Okay, so suppose it is the vertex lie in the real line. So the picture will be like this. So this is my delta, and these are my vertex angles. Okay, so this, suppose this is my triangle. So what we are first going to prove that, so area of this triangle is pi minus alpha plus beta. Yeah, so this is my real line, and this triangle is meeting. So one of the vertex of this triangle is on the real line, and it is x. So now we are going to apply this transformation here. So tz equals to your minus 1 by z minus x. Again, note that, so this t is an isometry of this upper half plane. So now, so t is an isometry of this upper half plane. So in fact, t is an element of this PSL to R. So t will preserve the area of this delta. So now if I apply this transformation here, so what we'll get, so we'll get the following thing. So we'll get this triangle. So t of x, it goes to infinity. And also this map t, so t is an element of this PSL to R also. So t is, again, it is a conformal map. So it will preserve the angles. So, okay, so if I name the geodesics of this triangle, earlier triangle, so by gamma 1, gamma 2, and gamma 3. So this is my t of gamma 1. So t of gamma 2, so this will be a vertical line. Because t of x is going to infinity, so this will be this vertical line. So this is my t of gamma 2. And t of gamma 3, again, it is a vertical line. So this is my t of gamma 2. So t of gamma 3. And this angle, so this will be my alpha. So this angle, so this will be my beta. And suppose the center of this semicircle is A. So then, so what we can do, so again, we can apply the a transformation. So let sz equals to z minus A. So then the earlier, this figure, so this thing, it will transform to, so if I apply sz equals to z minus A, so this will transform to, again, the same kind of picture, but the center of the semicircle, it will be at now at the origin. Yeah. So this is my S compose T of, let me recall. Yeah. So S compose T of this gamma 3, this side. So this is S compose T of this gamma 1. This is S compose T of this gamma 2. And this triangle is ST S compose T of delta. So again, note that. So S, again, it is an isometry. It belongs to your PSL to R. So this area of this delta, so this will be equal to area of S compose T of delta. Okay, so now what we are going to show that area of this triangle. So area of this triangle, so whose vertex angles are alpha, beta, is equal to your pi minus alpha beta. Okay, so now let us concentrate on this picture. This picture. So let us take this vertex to be A, this vertex to be my B. And so these are my verticals lines. So this line, let us take it to be x equals to A. And this line, let us take it to x equals to B. So join O to B by a straight line, O to A by a straight line. So this is a Euclidean thing. And so if I draw a tangent here, so angle between this tangent and this vertical line, so this will be equal to A. And if I draw a tangent here at B and take the vertical line, so angle between these two straight lines, it will be beta. So once again, so this angle is 90 degree. So this angle is 90 degree because I have drawn tangent, and this is the radius. So the radius. So therefore, can check that this angle, so this will be your alpha and this angle is your beta. Okay. So now we can compute this integration. So let the equation of this circle. So maybe I'll write it here. So let the equation of the semicircle containing the geodesic segment AB to be y equals to root over r square minus x square. So r is equal to mod of OA, and which again it is equal to mod of OB. So this is the Euclidean distance. And so therefore, so the equation of geodesic segment, AB is y equals to root over r square minus x square, and x is varying from A to B for some AB. Okay. So now, so what is my mu of delta? So this is equal to mu of ST of delta. So this is equal to this integration. So this integration we have to compute. So this integration is basically equal to this double integration A to B r square x square to infinity dx dy by y square. So we want to compute this area. So note that this x is varying from A to B, and y is varying from, so y is varying from this root over r square minus x square to infinity. So therefore, so this mu of delta, so this is again equal to integration A to B dx integration r square minus root over r square minus x square to infinity dy by y square, and which is again equal to this integration A to B dx by root over r square minus x square And now if we put x equals to r cos theta. So theta is varying from this pi minus alpha to beta. So the above integral, it becomes the following: integration pi minus alpha to your beta. So minus r sine theta. So dx is minus r sine theta d theta divided by r sine theta. So this integral is nothing but pi minus alpha plus beta. Okay, so therefore area of this triangle, so area of this delta in this particular case is equal to pi minus alpha plus beta. Now case 2 is the general thing. So case 2, so let delta be a triangle in H2 with vertex angles alpha, beta, and gamma. So we'll use case 1 to prove that this mu of delta is equal to pi minus alpha plus beta plus gamma. Okay, so let us draw this picture here. So suppose this is my triangle, geodesic triangle. So each of the sides are my geodesics. This angle is pi, this angle is your beta, and this angle is your gamma. So then what to do? So then you extend this side so that it meets the real axis. And now you join this point and this point by a geodesic. Okay, so now it'll get two triangles. So yeah, so one is delta, another one is your delta 1. Yeah, another triangle is this delta union delta 1. Okay, so let me write. So this is my delta and this is my delta 1. So this yellow thing, it is my delta 1. So delta 1 is a triangle discussed in case 1, and delta union delta 1, again it is a triangle discussed in case 1. Okay, so now note that, so this angle, so this total angle, so this is geodesic, so this total angle, so this will be my pi. So therefore, so one of the vertex angle of this delta 1, so this will be pi minus gamma. And let us take, so let this angle be theta. So therefore, so what we have, so mu of delta 1, so this is equal to your pi minus sum of the vertex angles. So one vertex angle is pi minus gamma and another one is your theta. So this by case 1. So also note that delta union delta 1, again it is a triangle discussed in case 1. So mu of delta union delta 1, so this is equal to your pi minus sum of the vertex angles. So the vertex angles are your alpha and beta plus theta. So pi minus alpha plus beta plus theta. So therefore this mu of this delta, so this is equal to your, so this difference, take the area of delta union delta 1 minus the area of this delta 1. So this is equal to, so pi minus alpha plus beta plus theta minus pi minus, again sum of these angles, pi minus gamma plus theta. So which is nothing but equal to your pi minus alpha plus beta plus gamma. So therefore we have proved that, so area of a triangle is equal to your pi minus alpha plus beta plus gamma. Okay, so as a corollary, so what we can say, so corollary, so let delta be a triangle in this upper half plane with vertex angles alpha, beta, and gamma. So then the sum of the angles alpha plus beta plus gamma is less than pi. So this is true because this area, this is always greater than 0. So this implies that alpha plus beta plus gamma is less than pi. Okay, so it follows from this equation. So mu of delta, if it is greater than 0, so alpha plus beta plus gamma, it will be less than pi. In Euclidean triangle, so this fact is not true. So the sum of the angles of the triangle is exactly equal to your pi. Okay, I'll stop here.